I'm Paul Hildebrandt, here to speak about automation of aircraft flight systems. Unfortunately, automated systems have been in the news in recent weeks. On October 29, 2018, Lion Air Flight 610 crashed into the Java Sea. All 189 people on board perished in the crash. Preliminary data suggests that a malfunctioning flight control system played a major role in causing the crash. The computer age has ushered in a rapid increase in the nature and capabilities of aircraft automation systems, and one of these new systems is at the center of the investigation in the Lion Air crash. However, basic flight automation technology in aircraft is much older than most people might guess. The first autopilot was invented by an American pilot named Lawrence Sperry in 1914. Sperry's father had invented a gyroscopic compass. Sperry rigged a hydraulic system to move the control surfaces of his biplane actuated by the gyroscope. Sperry demonstrated this system by flying over a crowd at a Paris air show while he stood on one wing of the plane and his engineer stood on the other wing, with nobody in the cockpit. In many cases, flight automation systems to this day are still based upon the idea of gyroscopes on airplanes sending signals to hydraulic systems or electric motors attached to the control surfaces. Modern autopilot systems can also take their guidance from electronic systems which replace the mechanical gyroscopes. They can also receive signals from ground-based radio stations called VORs, which give the system guidance as to whether the plane is on course either directly to or directly from the VOR ground station. The most recent navigational upgrades to autopilots involve the GPS system. Computers on the airplane can determine its position via GPS, calculate a course to any location on Earth without relying upon the existence of a VOR ground station, and then automatically control the airplane to the selected destination. While such a capability greatly decreases pilot workload and improves the efficiency of the flight, it is not without a few drawbacks. While the cockpit on the left may seem much more complicated than the one on the right, it is actually simpler and easier for pilots to learn. Each of those many dials tells a pilot only one thing. Each of the switches and levers accomplishes only one task. The airplane on the left does have some level of automation and a very capable autopilot, but the one on the right has a much deeper level of automation. It has only a few computer screens in places of all the gauges and dials of the older plane, but those computer systems are more complex and difficult to learn. A cockpit such as the one on the right provides a much more feature-rich and productive flight control environment at the expense of a much more complex training process and level of knowledge required to operate it. The most modern automated flight control systems aren't just for navigation and reduced workload. They can also take control of the plane when the pilot makes a dangerous mistake. One example is a wing leveling system. Even experienced pilots can become disoriented in clouds, bank the plane too steeply, and spiral into the ground. Wing leveling systems can and have saved the lives of pilots and passengers by forcing a plane's wings level when a dangerous degree of bank was sensed. Another very new type of automated safety system involves angle of attack correction. Like the wing leveler, it is designed to override one of the more common types of very dangerous pilot mistakes, which is responsible for a high percentage of aircraft crashes. The brand new airplane in the Lion Air Flight 610 crash was equipped with such a system. As this system has been mentioned in most of the very numerous news stories about the crash, it is helpful to understand what is meant by angle of attack and exactly what it is that this system was supposed to do. Angle of attack is defined as the angle at which the relative wind impacts the chord line of the wing of an aircraft. The top picture from the Federal Aviation Administration's Pilot's Handbook of Aeronautical Knowledge shows the profile of a wing at three different angles of attack. Note that in all three cases, the airplane is traveling in a straight line so that the air impacts it on and parallel to the dotted line at the bottom. Pilots control how much lift a wing produces by altering both speed and angle of attack. More of either of these variables increases lift. Increasing angle of attack comes at a price, though. It greatly increases drag and slows the plane. Additionally, there comes a point called the critical angle of attack where any further increase in the angle will cause a sudden drop-off in lift rather than producing more of it, a dangerous situation known as a stall. This is illustrated in the bottom picture from the Creative Commons and available as clip art in PowerPoint. The only way to avoid an imminent stall or to recover from a stall which has already occurred is for the pilot to push the nose of the airplane down to reduce the angle of attack. Pilots learn this from nearly day one in their most basic pilot training, and it is reinforced throughout training. Still, human nature being what it is, A high percentage of fatal crashes are caused by pilots who exceed the critical angle of attack, fail to push the nose down to recover, and stall the plane all the way into the ground, often developing an aggravated stall situation called a spin along the way. In recent years, angle of attack indicators have become a very common way to provide pilots with a visual indication of angle of attack, even in light private aircraft. On their 737 MAX, Boeing took a page from Lawrence Sperry's book and used a flight instrument as the controlling input for a new automation system. Engineers at Boeing used the angle of attack sensors to send information to automated flight systems, which adjusted the pitch trim, the nose up or nose down angle of the aircraft, to automatically lower the nose if the critical angle of attack was about to be exceeded. Tragically, the angle of attack sensors on Lion Air Flight 610 malfunctioned shortly after takeoff. They reported a near critical angle of attack when it did not exist. The automated control systems received the message that the angle of attack was too high, and they automatically adjusted the aircraft's trim to force the nose down against the pilot's will. Recordings from the crash show that the pilots tried repeatedly to manually readjust the trim, but the system kept readjusting it for nose down. A way to turn off the automatic trim controls did exist, but the pilots never turned it off. Eventually, they completely lost control of the aircraft and crashed into the water. Despite tragedies such as the Lion Air crash, aircraft automation systems have contributed overall to what can only be considered a stellar safety record for air travel. Where it used to take 3 or sometimes even 4 people to operate an aircraft's systems, it's down to 2 in modern planes. However, those 2 people must learn increasingly complex systems requiring extensive training to learn all aspects of those systems and become proficient in the use of all their features.